Okay, we're going to approximate functions using Taylor series. We know about our polynomial function approximation. We're going to look for, in this case, function of degree 4 that matches the behavior of f of x equals cos of x at x equals 0 through the first 4 derivatives. So in other words, p of 0 equals f of 0. First derivatives are the same at 0. Second derivatives are the same at 0, etc. So we've got a chart here. You can see we're asking you to find the value of the function cos of x at each of those derivatives. So obviously f of 0 is just cos of 0, which is 1. F prime of 0, remember that's negative sine of 0, which is obviously 0. F double prime is negative cos of 0, which is negative 1. Third derivative, sine of 0, which is 0. Fourth derivative, cos of 0, which is 1. Okay, so we found all of those values. Now, remember, we're wanting a fourth degree polynomial to approximate it. Reason being is for a lot of computer programming, it's easier to deal with a polynomial function than it is to deal with a trig function. So we're trying to find a polynomial. We can restrict it to a certain domain so that it almost exactly is the same, and then work with it to model different situations. You'll learn more about this as you go on in math at university. So first, p of x is given their coefficients. That's what we have to find out. What are the coefficients of all of those terms, each of the degree terms? So I'm going to take the derivative of all of them and then substitute 0 in for x for all of them. So first derivative, first term goes away. Second one is just a1 and plus 2a2x plus 3a3x squared plus 4a4x cubed. Second derivative then becomes 2a2 plus 6a3x plus 12a4x squared. Next one will be 6a3 plus 24a4x. And last one is 24a4. You'll notice those coefficients are factorials, right? So each time you take the derivative, just like when we learned about higher derivatives back in Math 31, each time you take a derivative, the exponent is a factor. So 24, for example, is 4 factorial. 6 is 3 factorial. 2 is 2 factorial. 1 is 1 factorial. Okay, so now we're going to substitute 0 in for each of those values. So p of 0 is just a sub 0. P prime of 0 is a1. P double prime of 0 is 2a2. Because we're just putting 0 in for x. So all the terms except the constant term go to 0. Triple prime, let me fix that a little bit here. Equals 3. I'll start using the factorials. Okay, and so that's going to help us now come up with our coefficients. So we've got those values. Now determine the coefficients of the polynomial function. So we know that the value here, okay, so this value here is equal to this at 0. Okay. So that a1 equals 0, then 2a2 equals negative 1, so a2 equals negative 1 half, or negative 1 over 2 factorial. Then 3 factorial, a3 equals 0, so a3 obviously equals 0. 4 factorial, a4 equals 1, so a4 equals 1 over 4 factorial, 1 over 24. Okay, so you can see a pattern in that. In terms of the polynomial function then, p of x equals 1 minus 1/2 x squared plus 1 over 24 x to the 4th. Because there are some coefficients that are 0, so those terms actually go to 0. So this is a 4th order Taylor polynomial. Okay, notice that if you even went to the 5th derivative and compared that, you wouldn't have another term. Okay, so in a way, if you're trying to approximate it more closely by taking one more derivative, it still would have the same approximation. If we look at the interval of convergence, so we're talking about f of x equals cos of x, a similar polynomial with an infinite number of terms. Right now we've only got 3 terms there, degree 4. But if we go infinite, for what values of x will the polynomial function closely approximate f of x? This is a question of convergence that we'll talk more about later, but we can use Desmos to help us out in doing this comparison. So we've got the general term for p of x. It can go on forever, right? So this is just the pattern that we found earlier. We only went up to degree 4. Now we have this going on forever. The general term then for this is n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. Let's take a look at that in Desmos. So I have them entered. You'll see the red is your cosine function. Your blue is the approximation. Right now, I only have it for n equals 0 to n equals 1. Okay, but it's very close. You can set basically from, I haven't got my scale going up by pi's, but remember pi is 3.14, so it's pretty. Okay, so as we increase our a value, which means we're adding more terms, you can see that the polynomial is approximating the cosine graph. Pretty cool how it can do that. Okay, so the more terms, the better in terms of an approximation of cos of x. So if we, as we know, I noted there, works pretty well from negative pi over 2 to negative pi over 2 to positive pi over 2. For that particular function that we just did, I put in Desmos the entire and went to, kept increasing the a value. If we look back at that again, if I just go to when I would get degree 4, which would be a equals 2, okay, you can see that for sure for pi over 2, it is an excellent approximation. So now, if we wanted to try to find the area under the curve for when x goes between negative pi over 2 to positive pi over 2, that would be another way of determining that it is a good approximation. So for this, I'm just going to use my graphing calculator. So here, if you take a look, I have it already entered. I have the cos function integration from negative pi over 2 to positive pi over 2. I get exactly 2. And then for the polynomial approximation, degree 4, I get 2.00904971. Rounds to 2, rounds to 2.0, 1 decimal place. Very, very close. Okay, so now if we want to approximate to a particular value of the corresponding function, so we just did cos from negative pi over 2 to positive pi over 2 of x, let's find the exact value of cos of 2. So this helps us determine how many terms we would need to get the exact value. So, or close to the values. Can't get an exact value of cos of 2. So I have on my decimals here. Sorry, I got to go back to. So there, I've entered that same polynomial function, but with an x value of 2. Okay, and going from 0 to a. If I start out at a equals 1, you'll notice I get a value of -1. Okay, well, cos of 2, if you do that on your calculator, is -0.4161. So I need to keep increasing a, the more terms the better. And so when I get to a equals 5, I get -0.4162. If I go a equals 5, sorry, I need to go a little bit further there. That is the closest, when a equals 6, with rounding, between a equals 5 and a equals 6. Okay, and that sum of all of those terms gives you the same value as cos of 2. So when we look back at our notebook file, number of terms, okay, so that really was when a equals, I think I said a equals 6. So remember, we've got x equals 2, n equals 0 to a, 1 to the n, 2 to the 2n, over 2n factorial. So when a equals 6, the sum is -0.4161. When I use calc, cos of 2 was -0.4161 to 4 decimal places. So therefore, your polynomial function be 1 minus x squared over 2 plus x to the 4th over 24 plus x to the 12. So think about that. A equals 6 makes that 12 as an exponent over 12 factorial. So now that we have a polynomial function that approximates f equals cos x, I want you to write a simplified 4th degree polynomial function that approximates cos of x plus 1. So now we're going back to that degree 4 polynomial function. Okay, so remember cos of x, degree 4 is 1 minus x squared over 2 plus x to the 4th over 24. So then g of x, now we would just replace x with x plus 1. So it'll be 1 minus x plus 1 squared over 2 plus x plus 1 to the 4th over 24. Okay, you can expand that out. Sometimes we'll leave it, sometimes we'll expand it out. If it's degree 4, probably we'll expand it. We'll have some like terms that we can deal with. So quickly do that. Remember that you can pause the video whenever you need to. Often with these polynomial approximations, we actually show it in increasing order of degree. So ascending order of degree. Okay. For cos of 2x, then h of x would be 1 minus. We'll just replace every original x with 2x. And simplify that. Okay, so you can check those out in decimals yourself and see that they approximate. Okay, we're going to pause right here. So we'll come back with example 2 and the rest of the note sheets.